Hello everyone, I'm going to explain the effect of temperature on reaction rate constant, and we explained what do we mean by reaction rate constant in a previous video. So let's start here. So as we know that the temperature is important factor that affect the rate of reactions, and usually, the rate of chemical and biochemical reaction increases with increase with temperatures, and this kind of dependence of reaction rate on temperature can be represented or modeled by Arrhenius type of equation, in which the K, the rate constant or the reaction rate constant equal to A, which is the frequency factor, and the times exponential of E divided by RT to negative sign. This A is again the frequency factor, and E is activation energy, and R is the gas law constant, and T absolute temperature. So keep in mind that this temperature is not really Celsius or any other type of units. It should be actually in Kelvin, which means absolute temperature in this case. And K and A should be at the same units, meaning that if you have first order kinetics, so A should be also using the units of the K, in this case per second, for example. And A is related to the number of collisions between molecules, and it's slightly affected by temperature in reactions, basically. And the for E is it's actually the activation energy, which means that the minimum amount of energy which the reactant molecules should possess for a reaction to occur. Means that you need actually to provide this kind of activation energy for the reaction to occur. Without this, the reaction, of course, will not be happening. And here, if you look at these figures here, we can find this clearly that the value of K increases with the exponentially increase with the increase of temperature. So now let's see how we can actually understand this better. So if you look at the previous equation here, this actually we can put it in linearized form. If we take the natural logarithm of the left-hand side, so ln K equal to ln A minus E divided by RT. And in this case, if we plot the values of natural logarithm of K against the reciprocal of T, in this case here, this is figures, we can actually find a straight line. A straight line means that you have the y-intercept, which in this case will be ln A, and the slope, which will be E divided by R. And here you can look actually in these figures here. For example, if you have this first rate constant K against the inverse or the reciprocal of T, means that you have actually different values, of course. So the slope here, if you have actually a high activation energy, this means that the slope will be very high, very large. And also, if you have low energy, so the slope will be a little bit steeper. And here, this actually, you can find this kind of trends. Of course, it can change against, because R is constant. So basically, the more energy you need to activate the energy, the higher the slope will be. And to calculate the E, in this case, if we calculate the slope, and then if we multiply by R, the slope by R give you the value of activation energy. Let's actually go to example very quick. So an example here, an experiment was conducted to determine the second order reaction rate constant at different temperature. Can you estimate the activation energy needed for the reaction to occur? So here, these are temperatures in Celsius, 24 until 48, and here this is the rate constant K. These values actually determined. Can you calculate the activation energy? In this case, here again, this put them in Excel. Here, this is temperature, and this is values, K values, and of course, as I mentioned, we have to convert the temperature into absolute temperatures. It means that you have to uh, convert these values to kelvins. Means that you need actually to sum or to add 273.15 to all of these values, give you the K in the temperature in Kelvin. And you have to get the inverse of these values, and you plot the value of natural logarithm of K. In this case, this again second order, and you can get this kind of line. Basically, after you plot the values, and then you can get the equation. In this case, you can actually have the slope. The slope in this case is 8,515, and you can get also easily you can get the E value or the activation energy if you multiply this slope by the value of, uh, of R, which is the gas constant or the universal gas constant. With that, I think I'm actually ending up this video and hope to see you again. Thank you.